All right, thank you, everyone. And thank you for coming out here bright and early. I'm not sure I would have made it if I wasn't here to speak. Before I begin, join me to give a huge thank you to Sam, Blue, Ben, Noah, Matt, all the staff who put this together. Making something like this happen is a lot of work, and I think we're all very grateful. So, as you all heard, I'm Cameron, and I'm the product lead for Go at Google. I've been a PM on the Go team for 3 years now, and it's really been the highlight of my career. I get to work with some of the most talented people in the world, and then I get to see a dedicated community like all of you actually use Go to build awesome products. And that community is really the best part, so thank you to all of you, and please keep it up. Today, I'm going to tell you about the state of Go. And the short of it is that the state of Go is strong. But before I tell you why, I want to recount how we got here. Now, I wasn't there, but the story is that during a 45-minute build, a C++ build, sometime in 2007, Rob Pike and Robert Griesemer scribbled together a vision of what would ultimately become Go. So according to Rob, a couple of Google employees had recently given a talk on all the new stuff that was coming up in C++11, and in the span of about an hour, Rob counted something like 35 new features that were being planned. Somewhere in there, he asked himself a question. Did the C++ committee really believe that what was wrong with C++ was that it didn't have enough features? Surely it would be a greater achievement to simplify the language rather than to add to it. So Rob made this observation in the midst of a period of tremendous growth at Google. The breadth of Google's products and services was growing, usage was growing, and then the engineering teams at Google that built and maintained all of it, they were growing too. So this slide shows us how Google's headcount grew between its IPO in 2003, when it had a little over 1,600 employees, to when Go 1.0 was released in 2012, when Google had over 50,000. So this meant a lot more people writing a lot more code, and coordinating all of that carried a lot of overhead. And since Google's business is all about scale, this problem was really only going to get a lot worse. And this is where Go was born. Google was kind of struggling with its scale, the complexity of a massive code base with so many developers working on the same projects in Java, C++. It led to brittle code and diminished productivity. And Go's vision was, hey, let's prioritize this scale, which means accounting for how modern software is architected, the environments in which modern software runs, and most importantly, the teams that write, operate, and then maintain it all. So on that basis, from when Rob and Robert started in 2007 to when Go 1 was released in 2012, the Go team worked to define Go's founding principles and build it for release. So this includes making it an open source project, which we did in 2009, and then ensuring that what we call Go 1.0 is usable, in part by putting it in production. So one of the key bits in Go 1's release notes was this emphatically stated point. The driving motivation for Go 1 is stability for its users. People should be able to write Go programs and expect that they will continue to compile and run without change. You know, some programming languages are good at this, some aren't. We're going to be really good at it. In fact, we released Go 1 with a separate document that explains our compatibility guidelines in detail, the Go compatibility promise. So there we wrote, it is intended that programs written to the Go 1 specification will continue to compile and run correctly, unchanged, over the lifetime of that specification. Go programs that work today should continue to work even as future point releases of Go 1 arise. And the reason that the compatibility promise is so important is because what we sought to release in Go 1 was not just a programming language, but rather a platform for software engineering. The vision wasn't to compete with C++ on the number of new features that we could release. The vision was to facilitate real-world software engineering at scale. You know, that sort of software, it's written in teams, where members come and go, where there are deadlines, SLAs, things like that. And that sort of engineering really requires long-term predictability, you know, not breaking existing code or creating a perpetual maintenance burden. It also requires accounting for the fact that software development is more than just the programming language that you use. It's this multi-stage life cycle with different intersecting tools. And that's the idea of a platform. So in addition to the compatibility promise, Go 1 shipped with all of this stuff on this slide too, all of it out of the box. So instead of importing a third-party library for testing or finding and agreeing on a style guide, Go 1 started on this mission of providing our developers an entire platform for everything you need to ship good software, scalable software in teams. And in what ended up being another important decision, the stuff that came out of the box was all accessible from a single command. So from the start, Go was very mindful of every link in the development chain, all the way up to the developer's command line. With the Go command, we established this first developer touchpoint, the entry into the platform, and one that continues to be a very important means by which we're able to ship unified end-to-end experiences today. So that was Go 1. Next, between 2012 and 2015, as developers were beginning to adopt Go, we focused our efforts on refining everything. And like any software project, the first few versions had a lot of rough edges, and actual usage helps you see that. And so for Go, this was like a multi-year process that culminated in 2015 with Go 1.5. So by Go 1.5, the platform was more or less refined. So for example, the compiler and runtime were completely rewritten from C to Go. It's sort of this important rite of passage for a programming language of this sort, where the compiler is written in the language it compiles. The garbage collector was another important or sore point in the very first releases. It was really slow. So we introduced a new garbage collector in Go 1.5, which reduced overhead and pauses to levels similar to what you saw in other garbage collected runtimes. Stepping back to the project level, it turned out that a predictable release schedule provided developers a lot of value because it allowed them to plan their own releases around ours. So Go 1.5 is the first version where we committed to our semi-annual release schedule, and that persists to this day. And more generally, by Go 1.5, the standard library was hardened, runtime performance was improved, and various other things were fixed or hardened throughout. But despite all this change, the compatibility promise from Go 1 applied. So as we wrote in the release notes, version 1.5 is a significant release, including major architectural changes to the implementation. Despite that, we expect almost all Go programs to continue to compile and run as before because the release still maintains the Go 1 promise of compatibility. Now, we saw on the slide earlier that Go 1 had a primitive form of dependency management, but in 2018, modules were introduced, which really represented a fundamental shift, one, in how Go code is written and packaged, and two, how Go code, especially third-party libraries, was distributed, and then the ecosystem that followed that. So to this distribution point, before modules, you would go get your dependencies directly from their origin on GitHub or wherever else. And the introduction of modules alone doesn't change that. But an important property of modules is that their contents for each version are immutable. And this provides opportunities for caching and authentication. So modules themselves were introduced in Go 1.11 and Go 1.12, along with the Go mod file and the Go mod command. And these things fundamentally changed how Go libraries are packaged and distributed. But in Go 1.13, we took advantage of that immutability property that I just mentioned to introduce the Go module mirror and checksum database. So with the module mirror, now we could cache all these libraries, and because we know they're immutable, we can serve them much more efficiently, which makes dependency downloads much faster, and by caching them, we can protect your dependencies from disappearing from their original locations. Separately, with the checksum database, we're able to now store a hash of all the source code in all these dependencies, which allows us to detect whether the source at the origin has changed since we first saw it, which protects against man-in-the-middle attacks and other sorts of tampering of your dependencies. Now, the module mirror and checksum database, they don't tell you whether a dependency has a vulnerability to start, but by recording the hash the first time any Go user downloads, imports the dependency, we can detect whether that module changes on any subsequent import by any user anywhere. So in this way, the module mirror and checksum database, they're able to ensure that the bits you or anyone else gets the first time are the very same bits that everyone gets on every subsequent time. And this capability, it started this new parallel consideration for our development focus. We realized that as Go was growing, especially in these huge, important infrastructure projects, the importance of security was growing as well. So in addition to being a complete, refined platform for software engineering, Go also sought to be a secure platform for software engineering. So we talked about modules and the module mirror and the checksum database. And around the same time as that, we started seeing a lot of really high-profile software supply chain attacks. This is the kind of thing where an attacker would inject a vulnerability in a commonly used open source library, and this would then affect wide swaths of a language ecosystem. Like you can think of log4shell in Java, for example. And that's where we really leaned into Go's security posture and its capabilities. So in Go 1.18, we introduced support for SBOMs, or a software bill of materials, and this means that the Go compiler writes into every binary that it builds all the versions and dependencies in the source, which then allows you to later verify that everything is correct with just the binary. In Go 1.18, we also introduced the built-in fuzzer, the first major programming language with native fuzz testing built into and integrated with its standard toolchain. You can think of fuzzing as a form of automated testing that intelligently manipulates inputs to your program to flesh out bugs, and especially security vulnerabilities. So because of the module ecosystem now, you can fuzz a specific version of a module, and if you discover a vulnerability, you can then report that, the results of your fuzz test, back to the package maintainer, and the maintainer can reproduce your results guaranteed. And then most recently, we launched our end-to-end vulnerability management system, which surfaces known vulnerabilities in your dependencies everywhere, from your IDE to runtime. So this last one just launched in July, and I think it deserves a little bit more time, so I'll elaborate on it later. It's really cool. Now, the introduction of modules and that security focus that followed, it coincided with another important development. Go was becoming increasingly important in industry. You know, for one, the entire cloud was being built on Go. So, this includes GCP, AWS, Azure, and all the different important tools and services that were becoming a core part of cloud-based development. Enterprises began to adopt Go as well, using it for these really important business-critical systems and infrastructure. I know some of you in the audience are actually from these enterprises. You probably know this firsthand. And inside the Go team, all of this use and adoption led to this sort of acknowledgement of Go's criticality, like this realization that attacks on Go can be particularly harmful, which then validated our focus on security and made it even more important. So I mentioned that a lot of security stuff came out in Go 1.18, but there was also this other important non-security related change in Go 1.18, which is, of course, generics. Generics were the single most requested feature of all time and the single most significant change ever made to the language. And in the years leading up to the release of Go 1.18, there had been a lot of talk about doing a relatively larger overhaul of Go that we'd call Go 2. And in fact, the compatibility promise that I showed you earlier actually specifically carves out a possibility for a Go 2, one that would be potentially incompatible with Go 1. And so leading into the work that eventually became Go 1.18, we realized this might be Go 2. Generics in particular, they were not only the biggest change we'd ever made to the language, they're likely the biggest change that will ever be made to the language. But it wasn't Go 2, it was Go 1.18. And the question that always arose with that caveat in the compatibility promise was, well, when will Go 2 happen? And the answer is never, or that it's already happened. There will not be a Go 2 that breaks Go 1 programs. There will be major revisions like what we saw in Go 1.5 and Go 1.18, but they'll never break your programs. Instead, we've actually doubled down on compatibility, which you may have seen in Go 1.21, released earlier this month, because it's far more valuable, we think, to to focus on compatibility than any possible break with the past. In fact, we believe that prioritizing compatibility was probably the single most important design decision we made for Go 1. So, as always, every release of Go has and will maintain the Go 1 promise of compatibility. And that brings us to today. Now, thinking back on that history I just laid out in that last section, you can imagine a series of layers that sort of build on top of each other. The core stuff like the language, the compiler, the runtime, standard library, they were all introduced in Go 1. And then modules, they were this paradigm shift that began in Go 1.11. And then our latest security focus, the stuff beyond modules, that really begins at Go 1.18, where we introduced SBOMs and fuzzing, and now we're on to vulnerability management. The next important piece to consider is how we continue to provide a platform. So earlier I emphasized the significance of the Go command in Go 1. There was this important developer touch point and the means by which we're able to ship this unified end-to-end experience. But along the way, we expanded into other important developer interfaces that enable us to really expand our definition of what it means to be a platform. So the Go command itself, of course, that's the original, the one you get at the command line. But our web properties, go.dev, package.go.dev, they also enable us to provide this rich experience for ecosystem discovery and documentation. For example, we recently added vulnerability data to our package site, which bolsters the ways in which we're able to deliver security-related information to Go developers, at more stages of the software development lifecycle. And more recently, in 2020, we took over ownership of the Go plugin for Visual Studio Code. This allows us to consider how developers can use the things that we build at the earliest stage of the work process, in the IDE itself. So when we released generics in Go 1.18, for example, we were able to ensure that generics were available in VS Code on day one. Vulnerability data, that was recently integrated there as well. So that's the platform as it exists today. Now let's take a look at adoption. So I'll start by saying that there are a lot of different ways to estimate how many Go developers there are, and it's really difficult to land on any particular way of measuring this. In this case, I've taken the proportion of respondents who report using Go on Stack Overflow's annual developer survey and then multiplied it by /data's estimate of the number of developers worldwide in any given year. And when we do that, the state of Go looks really strong. We have 4 times the number of developers this year than we did in 2018. And between 2022 and 2023, we took on 1.2 million new developers. That's a lot of new developers. And I'll return to that observation later. Existing developers are also extremely satisfied. So not only are we growing well, but once developers use Go, they're overwhelmingly satisfied with their experience. This is important not just because it validates our work or bodes well for future adoption. It also means a lot for team happiness, culture, recruiting and retaining talent. That's part of the core mission of optimizing for software that is built by teams. And we think there will be more of this to come. Go is consistently in the top languages developers want and plan to use, and 2023 has been no different. This slide from earlier this year shows that more developers said they plan to start using Go in the next 12 months than any other language. We're sort of like used to hearing this by now, but it's really remarkable, and I think it's a fantastic leading indicator of what's to come. Which brings us to how we think of Go today and the work we're doing now, and how we'll continue to pursue that core vision that started this project in the first place. All those things we've learned in the last 13 or 14 years, the things we've focused on, the impact we've had, it all sort of reduces to the mission and the title of this slide. Go provides the most productive platform for building production systems. It's productive because it's easy to learn and maintain and scale across teams. It's a platform because it's more than a language. It's an end-to-end developer experience. And it's production ready because it's reliable, efficient, stable, and secure. This framework is how we think ahead. Okay, So now for where we're going next. First is the work we have underway for making Go more productive. So we released generics last year in Go 1.18, but we continue to improve on it now, including in the standard library. We're also making ergonomic changes to the language itself, including a long-sought proposed change to loop variable semantics and another for standardized iteration. You may have noticed that we've included a preview of an experimental implementation of the change to loop variable semantics in Go 1.21, which, as I said, we released earlier this month. We're improving onboarding. As I said earlier, we take on a lot of new developers every year. From the Stack Overflow number I showed you, more than a third of Go developers only started using Go in the last year. And as we saw on the slide from earlier this year, more developers say they plan to start using Go this year than any other language. So we want to think of these developers and their experience so that they can quickly get started and be productive, and also continue to use Go productively after that as well. And I should say that we really think of onboarding here very broadly. You can even think of things like error messages, linking, documentation improvements. All of these things improve onboarding. All of these things help new users be productive, and the important side effect is that when we help these new users be more productive, we almost always help all users be more productive, including all of you. So next, we continue to think of complete, cohesive solutions that reach all of our developer surfaces. Remember, it's not just a language, it's an experience. So for example, this year, we started to survey package maintainers to understand what we can do to better support the package ecosystem. That's a huge part of what makes Go powerful today. We also continue to make our developer touchpoints more useful and robust. We recently actually made a bunch of really important scalability improvements to Go Please, you may have seen, which will make every IDE that relies on it substantially faster, especially for larger code bases that we're seeing more of. And our VS Code plugin continues to get better and more integrated, including by integrating with our new vulnerability management system, which brings us to vulnerability management, which, as I said earlier, we just launched into GA in July. So what is it? Well, we have a lot of more detailed materials on this online. It probably has a lot of its own talks, and I encourage you to look for all that stuff on YouTube or go.dev. But the short of it is that the Go team has created a comprehensive data source of all known vulnerabilities in the Go ecosystem, which we've done by pulling vulnerability data from a variety of places, like the GitHub Securities Advisories database, and then direct reports from Go package maintainers. Vulnerabilities from all these data sources are individually reviewed, curated, and then they're aggregated in the Go vulnerability database. And probably most importantly, we've made all of this data easy to find and use, most of all by integrating it across all of our developer touchpoints. So you can learn about the ones that might affect your dependencies on our package site, say before you start to use a dependency. You can use our command line tool to check at the command line or at CI. And then you can detect and fix vulnerabilities in your IDE as well through integration with our extension with VS Code. So this is our latest example of how, by focusing on building a platform, we're able to create these end-to-end solutions at all stages of the software development lifecycle. Finally, we continue to make Go production ready. Performance and reliability are a huge reason developers choose Go, and we want to be sure that we're still leading the way. So having doubled down on compatibility, we've taken steps to ensure that you can, if needed, emulate behavior from older versions of Go. So if the change to loop variable semantics that I mentioned surfaces a bug in how your code uses loop variables, we've made it possible to force compatibility so you won't have to worry about breaking when you upgrade. All this compatibility work was a big part of Go 1.21. On the performance debugging and monitoring side, we're exposing more metrics for the garbage collector. We're writing a garbage collector guide. We're working on execution tracing. And we're ensuring that Go works better with the Linux perf tool. And our standard library is seeing some really important new functionality as well, like structured logging, which Jonathan Amsterdam talked about in depth yesterday. Which brings us to the last section. So even if we're doing all of that work to make Go the most productive platform for production systems, why do we think we'll succeed? So the answer is actually right here. It's the Go's community. Since I started on the Go team a few years back, there has been nothing that has impressed me as much as the community and culture that all of you have built here. The Go project itself, not even counting the ecosystem, it's this vibrant and growing community of developers from all over the world who vote, they comment, and they contribute to this enduring project. There's also this large, robust library ecosystem as well, more than 1 million different modules. This is one of the most important things we have, and it's what we need more of. Quality libraries make everyone more productive, and they unlock these new opportunities that we as the Go team could never foresee. And we see Go really thriving in open source, which really bodes well as this leading indicator of what we think we'll see in industry next. So, programming language adoption, especially when you view it in the aggregate, it's fundamentally slow. A lot of stuff's already been written, and developers continue to maintain or improve on them. And it would be really inefficient for these developers to rewrite these workloads in a new language. Nobody wants to fix what isn't broken, and we don't want that either. Our objective, basically our opportunity, is to target new applications. So on this slide, we plot out the proportion of pull requests on GitHub by language per quarter for each of the major statically compiled memory-safe languages: C#, Java, Rust, and Go. So this isn't aggregated over the last 20 years like you'll find in a lot of benchmarks or surveys that ask developers, what languages do you use? This is like a quarter-by-quarter breakdown, sort of like a first derivative. And it's of actual work, because it's measured in pull requests. So as you can see, Go's ascent in red here, it's really pronounced. In the last few quarters, it's practically tied Java. And that's really so exciting for 2 reasons. First, because Go is growing in open source, it means that there will be more libraries for developers to use. That furthers that flywheel of productivity for all Go developers, and then furthers that vision of a really productive, secure platform for production systems. And even more than that, it means that Go and the Go community are really well positioned for the future, ready for those big shifts in technology that happen from time to time. Go and the Go ecosystem are better than ever, ready for those moments when new code is written. But for all that success and excitement, it always comes back to you, the community. So, we know that there are millions of developers actively using Go to build their applications, and we know that there's going to be many more to come. But even more than that, there are hundreds of thousands of Gophers around the world who meet up, they come to conferences like this because they love Go. That's irreplaceable. And that, most of all, is why the state of Go is strong. And that's it. Thank you very much, and I hope you have a great second day.